My name is Allie West, and this is a Lab 5, which I chose to do on collisions. So, quick introduction. In this lab, I will be demonstrating the motion of a collision system and demonstrate the conservation of linear momentum. I will be using Tracker to find my data for position over time, and basically what I will be testing is whether or not the system is really inelastic, meaning that energy is lost. So these are my principles I will be using: collisions, conservation of linear momentum, energy principle, and Newton's third law. So Newton's third law says every action has an equal and opposite reaction. Energy principle says that energy is always conserved. And then basically this is the conservation of momentum formula, which shows that the total change in momentum is zero. Therefore, P final or momentum final minus initial momentum equals zero, and then that means that final momentum equals initial momentum. So yeah, and these are the three categories for types of collisions. This is elastic, and this is inelastic. This is the procedure that I will be following in this lab. Okay, experimental data. This is the video I took this morning. Basically, I kick my soccer ball into my volleyball, and you can kind of see how they collide, and they both go their separate directions. So this is the data for the volleyball, which is red here. This is the x-axis, and this is the y-axis. And then this is the same, but for the soccer ball. Again, this is the x-axis, and this is the y-axis. And then all this data here I put into a spreadsheet, which can be seen here. And then I use that to help me find my initial data for the soccer ball using this formula. V1 minus V2 over, or change in velocity over change in time to get the first average velocity, which I use as initial velocity. And then these are my other starting data points. Also the mass, these are the masses of the volleyball and soccer ball. And then basically I use these graphs and then the data from them to create this chart, which shows this pink and red is for the volleyball, and this blue is for the soccer ball. Their x and y axes and just their change in position over time. This is the moment of the collision. You can kind of see how they kind of change directions. And yeah, and I got these. This is basically a combination of all these four graphs. Okay, so my calculations. First of all, this is where I found my final velocities using the same formula I used here. So I got these. And second of all, initial momentum equals final momentum. And then since we had two different masses, the first mass and second mass, initial equals the final of the first mass, the momentum of the first and the second mass. And then P equals NV. So that's why it's NV here on this line. And then basically I just input all the velocities and masses for the soccer ball and the volleyball from the beginning and the end. And then at the end, I got these two numbers. And as you can see, they're not equal, which this shows that the collision is inelastic and that energy is lost, because obviously like the energies are not equal to each other. So yeah, energy is lost due to factors such as friction and rotational energy, sound, I don't know, deformations, etc. There's a bunch of different ways energy could be lost. And basically this proves my point to be true, that the system really is inelastic, and that in a real life system, energy is usually not conserved within the system. So possible errors. It's a short video, which means there are less total frames, meaning less data points. So maybe it could be less accurate. Also, human error in Tracker, like maybe I didn't click exactly on the center of mass. As you can see, like it's a little bit blurry. Like I don't know, maybe that may not have been the most accurate. Also, I didn't do any mathematical calculations for K-Rot, which maybe could have provided some more insight. So what if, and further questions. What if the volleyball hit the soccer ball instead of the other way around? So I took another video and tracked it here. And notice, I'll play it again. Notice the position of the volleyball, how kind of sporadic it is. It kind of goes this way and then comes back around. And that's because it's it has a lighter mass, which means that it's more affected by K rot, or the rotational kinetic energy, which I think is why it spins back, kind of. I'll play it again. And on this graph here, you can see how strange its positioning is. So yeah, basically this means that although the system cannot be conserved, the energy is not conserved within the system, and in real life, basically, elastic situations don't exist.